Hello guys, welcome to this lesson. So in today's lesson, we are going to look at differentiation rules. Now, let's assume that you have been given a function, say f of x, to differentiate. Now you notice that we cannot just differentiate the function f of x here without knowing the rules that guides the process. Okay, so the differentiation rule serves as a guide that shows us how to handle different types of functions, and the rule also help us apply the right method depending on the form of the function that has been given to us. Okay. Yeah. Okay. So the first rule we have here is the power rule. And the power rule says that if n is any real number, then when you differentiate a function x exponent n, you're going to get n multiplying x exponent n minus 1. So what this rule is saying is that when you're given a function x exponent n, when n is any real number, then in differentiating this function, this n, which is the exponent here, the power here, will come in front here. Then you subtract 1 from the exponent. Okay, so you're going to get x exponent n minus 1. You get it? So let's solve the example below. So we have been given the function f of x, which is equal to 1 over x squared, and we are to differentiate f of x. So here our f of x can be written as x exponent -2. You get it? So our f prime of x is going to be -2 x exponent -2 -1, or -2 minus 1. So you're going to get -2 x exponent negative what? 3. Do you get it? Okay. So the second rule we have here is the product rule. The product rule. So the product rule says that if f and g are differentiable functions, then the product, which is h of x, which is equal to f of x multiply g of x, is differentiable. And when you differentiate h of x there, you are going to get f of x multiply the derivative of g of x plus g of x multiplying the derivative of what? F of x. You get it? So here, what we do here is, when you take a critical look at this, you can see that we hold f of x constant, then we differentiate the g of x, okay, plus the other side we hold g of x constant, then we also differentiate what? F of x. Okay, all right. So applying the same principle above, in this example, we have been given y to be x plus 1 multiplying x, and we have been asked to differentiate y. So in this case, our y prime, or dy dx, is equal to, so we hold x plus 1 constant. Okay, so we hold x plus 1, then we differentiate x, and when you differentiate x, you're going to get 1. You get it? We are going to get 1 because the x standing here alone is carrying an exponent or a power of 1. Okay, so when I differentiate, this one will come in front here. Then you subtract 1 from the 1, which is 0. So you get 1x exponent 0, which is 1. Do you get it? Okay, because x exponent 0 is 1. So 1 times 1 is still 1. Plus, we hold x constant. Then we differentiate x plus 1. Okay, so when you differentiate x plus 1, we are going to get 1. Yes, and the reason why when you differentiate x plus y, you're going to get 1 is because when you differentiate x, you're going to get 1. And whenever you differentiate a constant, you're going to get 0. You get it. Yes, so at the end, you'll be left with 1. So x multiply 1. So at the end, you're going to get a y prime to be x plus 1 multiply 1, which is the same as x plus 1, then plus x, which is 2x plus 1. They get it. Okay. So the next rule is the quotient rule. And the quotient rule says that if f and g are differentiable functions, then the quotient h of x, which is equal to f of x over g of x, where g of x is not equal to 0, is differentiable. And here, when we differentiate our h of x, we are going to get g of x multiplying the derivative of f of x minus f of x multiplying the derivative of what? G of x all over g of x all squared. So applying the same analysis here, you can see that here we hold h of x constant. Then we differentiate f of x, right? Minus we hold f of x constant. Then we differentiate g of x all over g of x all squared. So apply the same principle to solve this example below. You're going to hold x plus 1 constant, because here you can see that g of x was held constant here. So our x plus 1, we hold it, okay. Then we differentiate our f of x. Oh, please, sorry. Don't forget that our x here is our f of x and our x plus 1 is our g of x. Good. So when differentiate x, we are going to get 1 minus we hold our x constant, okay. When differentiate x plus 1, you're going to get 1. All right, as we did above, all over x plus 1 all squared. That is g of x all squared. So we are going to get x plus 1 minus x over x plus 1 all squared, which is 1 over x plus 1 all squared. We get it. So that's the quotient rule. Now, the next rule is the constant rule. So the constant rule says that if c is a constant, then when you differentiate c, you're going to get 0. So it means whenever you differentiate a constant, you're going to get 0. So example, we have been given our function f of x to be equal to 7. So our f prime of x, or the f dx, okay. So or the f dx here is going to 0. It's going to be 0 because 7 is a constant. We get it. Okay. So the next rule is called the constant multiple rule. So the constant multiple rule says that if c is a constant and f is a differentiable function, then whenever you are differentiating a constant, multiply a function, that is c multiplying f of x, we bring the constant out, then we differentiate the function itself, or the function that has been given to us. You get it? So example, here we are going to differentiate 3x exponent 4. Okay. So in differentiating this 3x exponent 4, what we are going to do here is to bring 3 out. Okay. Then we differentiate d, sorry, okay, that's d dx of x exponent 4. You get it? And when you differentiate x exponent 4, you're going to get 3 multiplying 4x exponent 4 minus 1, which is going to give us 3 multiplying 4x exponent what? 3. So you're going to get 12x exponent 3. We get it. Okay. And the next rule is the sum and difference rule. So the rule states that if f and g are both differentiable, Then whenever we differentiate f of x plus or minus g of x, then you're going to get d dx of x plus or minus d dx of g of x. So what this rule is saying is that whenever you're given two functions, f of x plus or minus g of x, and you have been asked to differentiate this function, okay, you can differentiate this equation part by part and be differently, like you get me. So it's like you multiplying through the d dx. Okay, so I can differentiate or differentiate f of x, okay, then plus or minus the differential of what, g of x. Do you get it? All right. So example, you have been given the function x exponent 4 plus 3 squared to differentiate. So our derivative will be d dx of x exponent 4 plus d dx of 3x squared. So when you differentiate x exponent 4, you're going to get 4x 4 minus 1 plus. So already, don't forget, you have 3x squared here. So we'll bring the 3 out. Then when you differentiate x squared, you're going to get 2x exponent 2 minus 1, which is going to give us 4x cubed plus 6x. Do you get it? Okay, so you have 4x cubed plus 6x as our answer. Now, we also have the exponential differentiation. Okay, so under the exponential differentiation, we have the natural exponential function, e exponent x. Now, when you have e exponent x, when you differentiate e exponent x, you still get e exponent x. Okay, so the reason you're going to get the e exponent x back is because when you're given e exponent x to differentiate, what you do here is to differentiate the function here, that or the function that e is carrying. Okay, so when differentiate that function that e is carrying, you come and put it in front here. Okay, then you write your e and you repeat or you write the function that e is carrying already. Do you get it? So here you can see that when differentiate x, you're going to get 1. So it will be 1 multiplying e exponent what? X. So in that case, you're still going to get e exponent x. Hope you get it. So let's have the example below. So we have been given e exponent x minus x to differentiate. Okay. So bear in mind that whenever you're giving e exponent x to differentiate, you are still going to get e exponent x, right? So applying the sum and difference rule, we can write d dx. Sorry, we can differentiate our function here by expanding it. So you're going to get d dx of e exponent x minus d dx of what? X, and you're going to get e exponent x minus 1. Hope you get it. All right, because when you differentiate x, you get 1. So and then you're going to get e exponent x minus 1. Okay. Now you have the general exponential function 2. Okay. Now you have the one with the base e. So we have been given the function a exponent x, where a is a constant. Okay, our a is a constant. So what you're going to do here is when you are asked to differentiate a exponent x, what you do here is you write your a exponent x again. Then you find the natural logarithm of e. So at the end, we are going to get ax ln e. Like, do you get it? A exponent x in a. So example, you have been asked to differentiate 2 exponent x. So what you're going to do here is you repeat our 2 exponent x, or you write again our 2 exponent x, then you find the natural log of 2. So 2 exponent x in 2. This is going to be our final answer. You get it? Okay. And you also have the exponential with a function in its exponent, e exponent f of x. Okay. So whenever you are given e carry a function, say f of x, then okay, so as I explained earlier, you differentiate the function that e is carrying, you bring it in front here, then you write e with the original function that was given to you. Do you get it? Okay, so example, you have been given e exponent x squared. Okay, so what you're going to do is differentiate x squared here. So when you differentiate the x squared here, you're going to get 2x. So we had 2x because the 2 will come for x squared, the 2 will come in front here. Then you subtract 1 from the exponent, which will give you 2x exponent 1, which is 2x. Okay. Then you repeat the function that I've been given to you. Or you write your e and you write the original function that e is carrying, which is what? X squared. You get it? Alright. We also have the derivative of trigonometric functions. So always put this in your mind that whenever you differentiate sine, you get cos. Whenever you differentiate cos, you get negative sine. Whenever you differentiate tan, you get sec squared, right? So when you differentiate sine x, you get cos x. Cos x, you're going to get negative sine x. When you differentiate tan x, you're going to get sec squared x. Now, when you differentiate cosec x, so the cosec here is 1 over sine, okay? 1 over sine x. So cosec x is 1 over sine x. So whenever you differentiate cosec x, you're going to get negative cosec x cot x. And our cot x is equal to 1 over tan x, okay? Yes. And whenever you differentiate sec x, you're going to get sec x tan x. And our sec x here is 1 over cos x. All right. And whenever you differentiate cot x, you're going to get negative cosec squared x. Hope you get it. So maybe at the right time, I'll upload a video on the proof of each of the derivative. Okay. So let's solve the example below. So we have been given f of x, which is equal to sec x over 1 plus tan x to differentiate. So if you look at this function that I've been given, you can see that you have to apply the quotient rule. Okay. So you're going to apply the quotient rule. So for the quotient rule, we get our f prime of x to be. We hold 1 plus tan x constant. So 1 plus tan x, so we hold 1 plus tan x. Then we differentiate sec x. Now, when you differentiate sec x, what do we get? So when you differentiate sec x, you're going to get sec x tan x. So here, you're going to get sec x tan x minus, we hold sec x constant. Then we'll differentiate 1 plus tan x. Now, we will apply the sum and difference rule here. So 1 plus tan x that you are having, when you are differentiating it, is same as d dx of 1 plus d dx of what? Tan x. So when you differentiate 1 is a constant, so you're going to get 0. Now when you differentiate tan x, you're going to get sec squared x. Do you get it? So you're going to get sec squared x. So here our derivative of 1 plus tan x will give us sec squared x. Okay. So all over 1 plus tan x all squared. Now when we expand this one, you're going to get sec x tan x plus sec x tan squared x minus sec cube x all over 1 plus tan x all squared. So what we are going to do here is to factorize sec x out. So when you factorize sec x out, you're going to get sec x multiplying the bracket tan x plus tan square x minus sec squared x. Okay. So let's work with the numerator. Then bring the denominator later. Okay. Now from trig identity, sec squared x minus tan squared x is equal to 1. Okay. Let's bring the right hand side of the equation to the left hand side and bring 1 to the left hand side. Okay. So when that, you're going to get negative 1 is equal to tan squared x minus sec x squared, sec squared x. Okay. And you can see that what we have here is the same thing as what is here. You get it? Good. So we are going to replace tan squared x minus sec squared x with negative 1. So our answer is going to be sec x multiplying tan x minus 1 over 1 plus tan x all squared. Okay, so that's our final answer. All right. Now, the next one is the derivative of logarithmic function. Okay, and it says that if y is equal to ln of g of x, then the y dx is equal to d dx of ln of g of x, which is equal to g prime of x over g of x. So what this is talking about is, now if you are having y is equal to ln of g of x, okay, then the y dx or y prime is equal to, you differentiate g of x, what is g prime of x over the original function of g of x. I didn't get it. So that's what it is talking about. So example, you have been given a function f of x, which is equal to ln of sine x. So our f prime of x is going to be, now we are going to differentiate sine x. And we know that when you differentiate sine x, you're going to get what? Cos x, right? So you're going to get cos x over the sine x. You get it? Now, from trig, sine x over cos x is equal to tan x. And we learned that cot x is equal to 1 over what? Tan x, which will give us cos x over what? Sine x. So in this case, our cos x over sine x here, you can see that it's equal to cot x. Do you get it? All right. So we have the derivative of inverse trig functions, okay, or trigonometric functions. And here, whenever we differentiate the sine inverse of x, we are going to get 1 over the square root of 1 minus x squared. So in some books, instead of sine inverse of x, you will see arc sine x. The same thing, okay? Or arc cos x, arc tan x. They are all the same as the sine inverse and cos inverse and the rest, okay? Okay. So when we differentiate cos inverse of x, you are going to get negative 1 over the square root of 1 minus x squared. So you can see that this one is similar to the derivative of the sine x, but it is having negative, okay? And when you differentiate tan x, you're going to get 1 over 1 plus x squared, okay? When you differentiate sec inverse of x, you are going to get 1 over the absolute of x multiplying the square root of x squared minus 1, okay? And when you differentiate cosec inverse of x, you are going to get the negative of 1 over the absolute of x multiplying the square root of x squared minus 1. So here too, we can see that the cosec inverse derivative is similar to the sec inverse. So the only difference here is the negative, okay? So that's the only difference. And when you differentiate cos inverse of x, you're going to get negative 1 over 1 plus x squared. So you can see that the cot inverse of x and the tan inverse of x, they are also similar, but there's negative in the cot, okay? So the negative of 1 over x, 1 over 1 plus x squared is the derivative for cot inverse of x. Now let's solve the example below. So we have been given the function f of t to be equal to 4 cos inverse of t minus 10 tan inverse of t, and we have to find the derivative of f of t. So here our f prime of t will be equal to, so we bring 4 out, then d dt of cos inverse of t minus, we bring 10 out, d dt of tan inverse of t. Okay, this is what we're going to do. I did this because, don't forget, we are going to find the derivative, sorry, d dt of 4 cos inverse of t minus 10 tan inverse of t. So that's why I expanded it to get this one. Okay. Now our f prime of t is equal to, so 4 multiplying, when you find the cos inverse of t, you are going to get negative 1 over root of 1 minus t squared. Don't forget, here we are using t, not x. Okay. Minus 10. When you find the tan inverse of t, you are going to get 1 over 1 plus t squared. Okay. So you're going to get negative 4 over the root of 1 minus t squared minus 10 over 1 plus t squared. Okay, so this is going to be our f prime of t. If you like, we can also simplify further. Okay, but let's leave it here. In our next video, we are going to solve few examples on the differentiation. Please, if you find this video helpful, don't forget to like, subscribe, and share. Thank you very much.